Okay, so hello everyone. Welcome again to the next class related to DRH, Radiative Transfer Code. Today is day 12, and as I said in last last class, we are going to learn how to compute response functions with RH. We will compute those response functions for the same spectral range that we defined in day 8. You remember it was the calcium 8542 spectral window, spectral line, plus the satellite lines that we defined in detail during those classes. We will compute in this class the response function itself. I will show you how to compute it for temperature and magnetic field. And then we will leave the interpretation of the response functions for the next class. You will see that I thought to do both things today, but I think it will take too much time, and I prefer to separate it into classes so we can do both things in a slower pace. And then I don't want to enter in details, but I fully recommend you to read a bit about response functions and also numerical ones. So I think a good introduction is Vasilius' paper from 1994. Also, you can read the third paper, but I think this one is very nice. So here you have the reference. And today we will do the computation of the response functions numerically. So I think it was explained in this publication, so you can look at it. I put it in the Dropbox folder, so you can have the PDF or just download it from here. And then just in a very brief way, so in the case of SER, we can solve the response functions analytically because they are in LTE. But things are much more difficult in non-LTE. So in previous codes and most of the inversion codes in today, they tend to use the response functions numerically. So they are computed by finite differences. But there has been some work trying to get as close as possible to an analytical non-LTE response function. So I think they call it in their works semi-analytically because they are not full analytical. But I think it's a very nice reading to read those two works, because you will understand why we in general use numerical response functions in inversion codes that work in non-LTE. And also why, in the case of this site, we decided to use SER as the main engine, and then we use the non-LTE information through the perture coefficients from RH. So I think it's an interesting reading. So please, if you have time, just take a look at it. In the case of miscellaneous, there are no updates or news, so I think this is good. So I think we can already go to the program. So we will work in two folders today. One is this response function -t, that is the response function to temperature. Again, it's always the same, so we have it in the RHF1D folder. And then we will have a second one that is response function -b, that is _v, that is the response function to the changes on the field strength. Okay, so let's start with the ones to temperature. The scripts are mainly the same, but there's a minor change. So we will cover one, and then we will cover in the second case the change only. Okay, so then let's start with this. So as always, I try to remove everything from the previous computation. And then what I say here is we are going to compute the response functions to changes on the atmospheric parameters at different heights. Okay, so we will do this for a given spectral range, that is the calcium 2 spectral window. Okay, so here the main concept, and I will go through it a lot, or I will go back to it, is that you want to understand how a profile, how a spectral line, or how the polarization signal of that spectral line changes or behaves when you change something in the atmosphere. So if you are in the sun and imagine that an event is happening, so there's a heating. So if your line is sensitive to that, to a temperature change on the place where the heating is taking place, it means that you are going to see changes in the spectral lines. So the idea is to try to quantify that sensitivity through a function. In this case, it's a response function. Okay, we covered that in the third course, but I think it's good to try to bring it here again, because it's the basis, the foundation of the SER and most of the inversion codes that you have nowadays, and in particular desire. Okay, so then for computing response functions, you need two things. So they are a 2D array. So you need an atmosphere, because the information it's dependent on height, and also you need a spectral range. Okay, so in the case of the atmosphere, let me see what I say here. Yes, so then as the response function, it's height dependent. It depends on the atmosphere you use. So if you pick an atmosphere that is, for example, a FAL model, that is a quiet sun model, you pick an atmosphere that is corresponding to a sunspot umbra, the response functions are going to be different because the temperatures are different, the magnetic field is different. So the idea is that if you want to compute the sensitivity of a spectral line to a given atmosphere, it's fine. But if you do that only, you cannot assume that in another scenario with a very different atmosphere, the response function is going to be the same. Or the other way around, you can assume that it's going to be different. So always try to compute response functions with standard models and have this as a general idea, or you can go to an atmosphere that is representative of a scenario that you are interested on, and then you will have a response function for that specific case. But please always remember that response functions depend on the atmosphere that you use for computing them. Okay, so in our case, we are going to use a simple atmosphere, the FAL-C atmosphere that we have been using since the beginning of the course. And we are going to add a very simple magnetic field that is constant in strength, inclination, and azimuth with height. But as a homework, I recommend you to try to repeat the same process that we are going to cover here, but using a different atmosphere. For example, one from BIFROS that we have a lot from previous classes. Okay, and then before starting anything, I want to comment on something, and the idea is in the case of non-LTE atmospheres, usually we have that the vertical domain is not uniform. So we tend to put more points on the chromosphere and less points in the photosphere. This is essentially because we don't need so much points in the photosphere and we can save time. It's the same as with the spectral range. If you remember, we were solving with higher density the line core of the calcium line, and with lower density of points the wings. Alberto, yes.
So that comment that you have made right now is true if you are only considering, in this case, calcium, what is sensitive in the chromosphere. But if you are considering multiple lines, let's say 601 and 8542, then you have to have a more or less constant grid, right?
Not necessarily. So the idea is that the grid in the photosphere for the FAL model is enough for any photospheric line. And the grid in the chromosphere is dense enough for any chromospheric line. So I think it's okay as it is. So I mean the photosphere is not very coarse. It's just that I think the points are every 30 or 40 kilometers.
I understand. And I understand that, but I guess if you are considering several lines simultaneously, that you want to distinguish whether it's the contribution of the photospheric lines at different heights. I I don't know. I don't think it's having just few nodes in the photosphere when you have maybe, I don't know, 5 photospheric lines.
But I think
at different heights.
Yeah, so I think these are not nodes. So these are points in geometrical height.
Yeah. I understand. Is the sampling grid in the okay.
So I understand your comment, but what I mean is that if you look at the FAL model, you will see that it has in the chromosphere, I think, points every 2 kilometers or every 5 kilometers. And you don't need that for photospheric lines. So I think the model is, well, we can look at it. So I think it's easy if we just...
No. It's okay, Carlos.
Okay.
Don't worry.
so what I mean is that if you see here, this is the upper layer. So you see that every 2 kilometers, you have points in the upper layers. But then in the lower layers, you have like 50 every 50 kilometers. Okay. So then what this means is that for a photospheric line, every 50 kilometer step, I think is probably enough. Although you can always interpolate this to a finer grid. And then the model has a very, very, very dense grid in upper layers. Okay. So I think it's a balanced atmosphere. You can always add points, but the concept is in the photosphere, probably every 50 kilometers, you are solving any photospheric line. And in the chromosphere, if you have every 50, it's not enough. And with the one that we have, every 2 or 3 kilometers is fine. But if you do the atmosphere with the every 3 kilometer step, then your atmosphere is going to be like 1,000 points. And this is really very time consuming.
Yeah.
Okay.
Thank you very much.
Yeah, thank you. So then the main idea is that I think following Alberto's question, I think you can even increase the density of points in the atmosphere of the FAL model, but I still recommend you to have a coarser grid in the lower part of the atmosphere and a denser grid in the upper part, because it will save time. So this is what we are going to do today. So this has an impact later, and I will try to show you later an example, and in next week or in the next class, we will cover it in detail. But the idea is that if your height domain is not uniform and you try to make a 2D plot of that result, I think at least with IVL, you will not see the real behavior. So if you do a 1D plot in IVL where one axis is not uniform, usually it works. But when you have a 2D plot and one axis is not uniform, at least the procedures that I use, they assume that every axis is uniform, so you are not seeing the response function properly. So in that case, what I'll always do is I save time in the computation. Instead of having a uniform step, I have a non-uniform one. And then I interpolate the result to a uniform step grid. Okay, and this is what we height grid, and this is what we'll do in the next class. So just be careful about that. I think it's not only response function, but in other cases, when you have a 2D array and one of the axes is not uniform, I think doing a 2D plot of that should be done with care, because you may be representing things that are not exactly like they should be. Okay, I don't know if I was clear. I will try to show you later and then in the next class. Okay, so then having that in mind, we have an atmosphere. We are going to read it with RH and we are going to save it with this name, and then we just save it. And I will show you later why we want to save it in this with this name. Okay, so then we have that we need to define the number of the geometrical height points, and we just get it from the previous structure. And then we want to compute response functions to temperature and magnetic field. So in this case, even if we are going to focus on temperature first, we need to have the magnetic field, so then the computation is consistent. So let's define a very, very simple magnetic field with a field strength of 500 Gauss, and then an inclination of 45 degrees and 70 degrees, and everything is constant with height. And then we just define it, we just save it as IRH file using this ideal instruction from RH. Just remember that the field strength should be in Tesla, and then inclination and azimuth should be in radians. Okay. Then in this case, as we had from the previous class, we selected the calcium window, and we found it in, I think, in day 9, that it was between these 2 points. So just I'm going to focus on this spectral range. Okay, and now let's define the, let's say, the response function ingredients. So again, as I said before, the concept is relatively simple, but I will try to show you how we're going to do it. So the idea is that we are going to compute the Stokes profiles after adding a perturbation in the atmosphere at a single height. Okay, and in this case, this height will be every point. So after adding that perturbation, we are going to add the same perturbation with positive sign, and then we are going to add in the initial atmosphere the same perturbation but with negative sign. So we are plus and minus perturbation. Okay, and we compute the Stokes profiles in each case. And then the response function, the full spectral domain at that Zi height will be the difference between those synthetic profiles weighted by a constant value. Okay, so we have an atmosphere, we change in one height, compute the profiles. We change in the other direction at the same height, compute the profiles, and then we compute the difference between those profiles. Okay, and this will be the response function over the entire spectral range, but at this height. And then we're going to do the same, but for a different heights. Okay, so then the array we are going to store at the end will have the spectral range dimension and the height dimension. Okay, and then before starting the loop that we need to execute, we need to define the amplitude of the perturbation. And in this case, I think there's no strict rule of you need to use this value or that value, but I think it should be really small compared to the complete value of your atmosphere. So if you remember, in the photosphere, we are around 5,000 to 10,000 something in the chromosphere. So I think having a perturbation between 1 and 5 Kelvin should be enough. So you will see that with this small perturbation in temperature, if the lines are sensitive to the temperature, you will see a change in the response in the profiles, and then you will have a value different than 0 in the response function. Okay, so again, try to have a very small value, but there's no strict rule of which one you should use. Okay, and now we start on the response function computation itself. So as I said, the idea is we will have the full spectrum, so the wavelength dimension of the response function every time that we call RH. And then we need to call RH twice, when we perturb with positive and then when we perturb with negative perturbation. But then we need to repeat the process for every height. So then the loop is going to run for all atmospheric layers. And inside each loop, we are going to call RH twice, with a positive perturbation and a negative perturbation. Okay, so then trying to make it simple, I just define in this case one array that I call parameter up because it's a positive perturbation, parameter down because it's a negative perturbation, although I don't know if the names are the best thing. And they are the atmosphere, the temperature that is defined outside the loop. So every time that we run the loop, we will go back to here and we will restart this the value of this parameter up and down. Okay, so then we start the positive perturbation, and what we do is we take this parameter up that is restarted and is reset, and then is the original temperature from the FALSI model, and only at a given height point, at a given index, we add the positive perturbation. Okay, so it's just 1 point, and the rest is the original FALSI model. And then we need to save that new atmosphere in RH format. Okay, so then we save it, just define everything as in the original format. Okay, so this Atmos RF is what we defined outside the loop, and everything is Atmos RF dot something except the temperature that you can see here. The temperature is equal to param U, the param up. Okay, and then we write atmosphere. We call RH. We solve the ray for mu equal 1, and we read everything. Okay, and then our let's call it Stokes I up perturbation. It's the ray information I Stokes Q U and V in the wavelength range of interest. Okay, and now let's try to do the same but with different with the opposite perturbation. So we have parameter down, and again in this case we just change it on a single index, and we subtract the perturbation. In this case is 1 Kelvin. We save the atmosphere, and as before, everything is the original FALSI model except temperature, that in this case is parameter down. We write the file, and then we call RH again. And then we store the Stokes profiles from the perturbation down, that is negative perturbation. Okay, and again it's only in the spectral range of interest. So with that we can compute the response function, and the response function are simply the difference between up and down, Stokes I, Q, Q, U, U, V and V, and then they are weighted by a factor, and this factor is 1/2 times the perturbation. Okay, and I think you can see that in equation 3. So I think we can just let me check. So equation 3 is this one, and this is the constant value that we are adding, that is here. Okay, and then what we are doing, just to try to emphasize what we are doing here, is that in this case optical depth, but we are going to is the same in geometrical height. So every time that we compute the difference between the two calls, the two synthetic profiles from RH, we are getting this row. Okay, and then we change height and we get a different row. So inside the loop, we are computing a row of this array, this matrix, and then the loop is running for all the rows of this matrix. Okay, and then with this we can just finish, and then we will get the response function Stokes I, Q, U and V to changes in temperature in this case. Okay, so I think I can quickly summarize this and then go to the field strength, but the idea is simple again. So the response functions are 2D arrays, wavelength and height. And numerically, we compute the wavelength dimension, calling RH after perturbing the atmosphere with a positive perturbation and a negative one. The difference between those profiles is going to give us the wavelength information of the response function. And then we repeat the process, calling RH after perturbing up and down for all the heights. And then it means that we will have the wavelength and height domain for the response function. Okay, so then I think I opened this, but this was just to show you that we are using the same information as before. So then just let me show you why I separated temperature and magnetic field for the computation. So the idea is that the script is essentially the same, but if you remember so until here is the same, but if you remember from previous classes, the RH reads the let's say, thermal information, temperature, electron density, velocity, microturbulence, hydrogen populations from the atmosphere. But magnetic field strength, inclination, and azimuth, they come from a different file. So then if you want to compute the response functions to field strength, you repeat the same script, but here parameter up and parameter down are now field. Field, if you remember, is defined here. It's here. And then the idea is that now you need to use the way of creating the RH magnetic field. So the thermal part is unchanged, but now we are changing the .B part. So then in our case, what we are changing is the field strength. So this one is the one is changing, okay? So then the program is essentially the same, but it's just that you need to save the change in the atmosphere through a different file. And then the same can be done for the parameter down, okay? And then the computation is the same. So you compute the Stokes profiles after adding a positive perturbation, the Stokes profile after adding a negative perturbation, and then the response function will be the difference between those profiles weighted by the factor that it is the amplitude of the perturbation. Sorry, I forgot. In this case, it's also the same. So if you remember, the field strength that we picked was 500 Gauss. So then you can use, for example, 1% of the amplitude, and then it will be a perturbation of 5 Gauss. And I think with this is enough for computing the response function with accuracy. So then I think this is basically what I wanted to say. And just again remind you that I separated in two because the atmosphere is divided in two as an input for RH. But the idea is that with the first one, with this procedure, you can compute the response function to any thermal parameter. So if you want to change the electron density or you want to change the velocity, just change it here and compute the response function. And if you want to compute the response functions to inclination or azimuth, you can use this script. So in this case, the parameter up and down could be inclination or azimuth. And then instead of changing this first part, you can change this inclination or azimuth. So then the three components of the magnetic field, you use this script. And the rest of thermal parameters, you use this script. Okay. So when you finish, this one is relatively fast to do. I think it will take like 5 minutes to do in a normal computer. So when you finish, you will get the results. And we have it already, but the idea is that what we want to do is something similar to what we had from the third course. So this, if you remember this, I think is class 3. In this case, is the response function to changes in the field strength, Stokes B response function to changes in the field strength for the two iron lines. So then in this case, you had Y was almost 0, so no sensitivity. And then in this case, red and blue, because the Stokes profile for the magnetic field constant with height that we picked, they are asymmetric. So then when we increase the magnetic field, the lobes, one goes higher, more positive and the other more negative, and the opposite happens when we decrease the magnetic field. But if you plot the raw response function that we have just created, it would look like this, okay? And here there are several things that I wanted to show you with count, slowly. So the first thing is that in RH, we are providing the atmosphere from top to bottom. So we need to reverse the axis. This is very easy and quick to do. But as I said before, here you have that the array, it's given the same space for all the points in the vertical domain. But the actual sampling, it's much denser in the upper layers than in the lower layers. So we need to use a different program for plotting that I think maybe there's one that can do this better, Or what I usually do is just interpolate again these results to a uniform grid and then check how it looks. And it should look probably closer to what we have in some publications from the past. So, but I would like to do this carefully and also showing you 1D plots, something like, just let me go back to this paper. So we may try to do something like this, where we picked different wavelengths that are represented here with color, and we see that they contribute essentially to a certain range of heights, but not other heights. So this will be what we will do in the next class, and more things that I will explain later. So before going to the summary of the class and the next things we want to do, is there any question from your side?
Carlos, so in the response function diagram for 8542 you showed us just now.
Yes.
Yeah, that one. Why it shows the sensitivity at the continuum of this line? Are we expecting this? I mean, if we look the continuum, I don't. Continuum of 8542, yeah, that part.
Yes.
Are we expecting any sensitivity at that part?
Yeah, I think, well, I mean, this is, I think is not exactly continuum. So the axis I think is wrong. So let's wait until next class where we have the correct axis. But I think not exactly continuum, because the lines are not sensitive to the continuum, but having sensitivity from the wings to changes in the magnetic field. So sensitivity in the wings of Stokes V to changes in the field strength, it's okay. So the line is sensitive to the field, to the magnetic field in the photosphere through the wings. But as you see with the colors, the sensitivity of the photospheric lines is larger than the wings of the calcium lines. But you should expect sensitivity from the wings at, I don't know, 100 kilometers to 100 kilometers to the magnetic field.
Okay.
Yeah.
It's basically a slight shift of the spectral line because of the Doppler or the Zeeman splitting. So yeah, that's what gives you that signal.
Yes. Yes, I think I will check the plots and we will redo it. But in this case, I think this I trust more. And the idea is that if you go to Stokes V response functions to, for example, VZ, that this is a different computation, but you see that here the sensitivity is very large, but it's not zero here. You can see this is locked out, but it's not zero. So the line, the calcium line, is sensitive to a very broad range of geometrical heights and optical depth. But it's true that it's more sensitive to changes in the upper layers than the wings, because the line is also very broad. But the sensitivity is not zero. Okay.
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 I have another question.
Yes.
So what is an advantage to have to compute the response function using the symmetric perturbations? I mean, does it make any difference mathematically if we just computed one perturbation and compare it with, I don't know, some reference unperturbed intensities in the program?
So you mean that instead of adding positive and negative, just adding positive?
Yeah, exactly. Yeah.
I think, Basilio, I think it will not work, right? Or yes? I think you're muted. I think we need both, Dato, but no, I think you're still muted, Basilio.
No.
Now. So what did you say?
Yeah, I'm not pretty sure. I don't know.
I think, Han, what do you think? I need to check. I think usually we add.
I think when I do it, I usually just use positive perturbations. I usually perturb by 1% and then compare to the unperturbed atmosphere. So so you just do the perturbation twice, or because you do it on both sides and divide by 2.
Yes.
Okay.
Yes. Yes.
The reason
Yes.
why I'm asking is if you use one single perturbation, then it will have your computation time,
Yes.
is it?
Yeah.
Yes.
Okay.
Yes. Yes.
Right.
Yes. Yes. So then in that case, you need to do the synthesis one with the original model, and this will be the one you compare to. Okay. Okay.
All right.
Okay.
Yes.
Thank you.
So it's half the computations plus one extra for the reference.
Yes, that's true. So I think I need to check if there's any difference, because why are we doing this way, Vasily? I think we
If it's as always, it's a compromise between the size of the perturbation and the noise. If you use a big perturbation, you have less noise, but in this case, you need to make central differences.
yes, yes,
Because it's not a linear function.
yes,
If you take a very small step size, you can avoid doing two perturbations because you are evaluating the response function in the middle of the perturbation.
Yes.
In fact,
Yes.
you are shifting.
yes,
Okay.
yes. So then we are including a bigger amplitude in total of the perturbation, but during the synthesis is half. So then we are being conservative in the sense of the perturbation that we add in, but then the difference that we are computing comes from a essentially bigger perturbation, right?
Yeah. The question is you have enough sensitivity in the synthesis in order to if you introduce a very small perturbation, you can have a noisy result. But in this case, you are evaluating the derivative.
Yes.
Correct.
Okay. Yeah. Okay. Okay. I think there's another question from Ryan, I think.
Yeah, I just really quickly wanted to ask, I didn't realize that computing these numerically was so manual. And I was wondering, does Desire have any functionality to do this over a field of view? Or are you still looking at cycling through for every pixel, every depth point? And
So Desire computes the response function in the same way as SER, so you can do it in parallel, but Desire is not computing the numerical response function that we are computing here. So it's computing the NLTE response function corrected by the departure coefficients from RH, that I think it's close, but it's not the same. Right, Basilio?
Yeah. So, because we are not changing, we are not considering the change of the departure coefficients. We are ignoring this part. Then we are obtaining an approximation, an analytical approximation of this numerical procedure. This is the right solution, the numerical one. And we are getting just one approximation of that.
Yes. So if you
I can just mention that, for example, a stick has that functionality. You just say, I want the response function, and it makes everything from the model that you introduce. And other comment I would like to do is with respect to the comment I previously made about the sampling. I was confused because I was thinking in log tau, that the atmosphere was given in log tau, not in geometrical scale. And that's why I was a little bit wait. I mean, it was my confusion. But usually except for numerical simulations with observational data, basically the atmosphere is given in log tau when you obtain the atmosphere from an inversion, right? So basically, I mean, I think it's the first time I see the response function in geometrical scale.
Well, yes and no. I think, I think except observation,
it's totally fine. It's totally the concept is exactly the same, but it was for me.
Yes. So I think two things before I forget. Well, let's finish this and then I go back to Ryan. And I say it here, but I forgot to mention it. But I think I said it in. Yes, so here. So I think here is what I mentioned, that today we are going to use geometrical height. In principle, you can use optical depth, but in case of RH, you could also use mass column as a as a height
that's
parameter.
Yeah.
But in my case, I think mass column, it will be much, I think it will be difficult to understand. In the case of geometrical height, it's okay because you know, and optical depth, we are used to work in optical depth, so we associate optical depth like -4, -5. But in fact, the one that should be more intuitive is geometrical height, because you have an idea of kilometers, while optical depth, we have an impression that, but this in general changes on the atmosphere. So I think it depends. In the case of RH, I prefer to use geometrical height. The only thing is that you should be careful to have a reasonable step, because kilometers and optical depth, they are different. So in the case of optical depth, I think 0.1, locked out 0.1 in the full range should be fine. And in the case of geometrical height, you can use the FAL model that we have here. Or if you feel that 50 or 20 kilometers, it's not enough in the photosphere, then you can interpolate this a bit more. But definitely you should not try to have 1 kilometer step, because otherwise you will add noise and the computation will be really, really long. Okay. And then Alberto, I go back to Ryan, and then if you have any question, just let me know.
Yes, sorry for
No, it's fine. So Ryan, the idea is that yes, so it looks very manual, but if you prepare this, for example, if you don't use IDL, just try to replicate this script in Python, and it will be very easy to do. And the idea is, as always, so analyzing response functions require effort, because you have to really look at the details. So then you can try to do it for multiple pixels, but I think it's, if you have a representative pixels and you do it like 5 or 10 atmosphere, it should be enough. So then doing it in this way, it's not so bad if you're not doing many times. And the truth is that, so numerical response functions are the most accurate ones that we can aim for. And these are or computed manually from RH like we do here, or as Alberto said, if you use code that use RH and numerical response functions for the inversion like stick, they do it internally and then it's an output. But in this case, we are doing it manually because we are just using RH for computing response functions. But my advice is that, so non-NLTE response functions will take a lot of time. So I think doing it manual for 5 atmosphere, it's something doable, although not comfortable. But the key thing is, these are the best ones that we can obtain, and they are in principle different and a bit more accurate than the ones from this side.
Thank you, I understand.
Yep. Okay. So any other question regarding this or other things that you could have in mind?
I would like, if it is possible, as you can see, I have many questions today. And
yes,
this is because I have been struggling lately with with computing response function. Okay. And considering that I have the experts in this meeting, I would like to, if it is possible, to show you some response functions and ask your opinion. Okay. Because I'm doing something that I think I'm doing right, but it's a little bit weird sometimes. So okay. Can I share my screen? Can I ask this question?
Do you want? Okay. I think it's fine. So that I will stop sharing. Yeah, and you can. Just be careful. We are recording, so just be sure that what you're going to show is response functions. Take your time.
I know. It's a presentation. It's a presentation I gave last week in Hinote Iris meeting.
Okay, then I trust.
No, I mean it can be bad, but it's now public. So what I have tried to do is the inversion or simultaneously of carbon 2 lines, the magnesium H and K, and the ultraviolet, and several photospheric lines, okay, that there is in the spectra of Iris. And they are inverted simultaneously. So at the end, you have a model that the synthesis should fit quite well all these lines. This is a couple of examples. Of course, not all are. And what I'm showing is different profiles at different locations. Basically, it's an active region, and you have in the umbra, penumbra, plus, and quite some. Basically, is that.
So Alberto, just 1 second. So black is the profile that you get from the code, and pink is the observation. Okay, so the fits are in general
Yes,
good,
this is
right?
iris are quite good in most of exactly that's what I'm going to show you. I think next slide. There are always challenging profiles, of course, as you can see. So yes, the black is a stick solution, and the magenta is the observed. But sometimes the observed profiles are quite challenging. So so well, as you can see, for example, here you have super broad carbon 2 lines. So then I decided to do the response function, and here is Basilio's paper with this beautiful sentence that explains carefully what a response function is. And here is the response function for the line. So this is just overplotting the line associated to this model. Okay, so this is the response function to the model. This is solid temperature. And for these different lines, as you can see, this is photospheric, this is the ultraviolet, triplet ultraviolet, and this is also photospheric. But these lines are in the winds of the magnesium HK, so the opacity is very high. So maybe you are going a little bit higher, and this is mostly in the continuum. This is lines very photospheric. So my question is that, well, and this is for different models, for these different, so it's showing what you, Carlos, were mentioning, that any model is going to have their own response function. But I was a little bit surprised that sometimes I have, I mean, this is in this color bar, I have tried to mimic this. This is the response function for 602, sorry, by Jose Carlos and Basilio in the review. So sometimes what I have not very clear is like, okay, you have still sensitivity here, right? You are, again, this is going a little bit higher, but most of the sensitivity, for example, in this line, it says it's come from the continuum, right? This is, oh no, sorry, this is the other way around, the color. So my question is, do you think that is related with my previous question, the very beginning confusion? We can do that with a model, make the response function for all these lines simultaneously?
Yeah, yes. So in fact, I can do it very quickly. So if you send me the atomic information, because I guess carbon and magnesium are solved in NLTE, right? And then,
no, I mean, this is I mean, this is what I did. And my question is if conceptually is appropriate, especially taking into account what I was mentioning about the sampling in the model atmosphere. I think this is correct, but I don't know if you need to change the sampling. It's just your comment, your first comment, one of my first questions.
So which sampling did you use in optical depth?
This is log tau, and this is 0.2, I think. This is 0.2. This is, yeah, I think, in the stick, well, the mode.
Yeah, so yeah. If you ask Basilio, when we were doing tests with the response function, he was using 0.05 and sometimes 0.005 for response function computation and comparison. So if you are going to just compute the response function for doing a test and comparison like this, I would go at least 5 times to the -2. Or even,
okay.
Yes. For the inversion, you have to do a trade-off. But if it's a computation like this where you want to have the information, I think 0.2 it's probably a bit coarse, mainly for the chromospheric lines. So 0.1, we do in my case, I think for the inversion, 0.1 is reasonable. But I would be happier if we have like 0.01 for a computation like this, because as I said, it's usually like 5 minutes, but if you increase a factor 10, it will be like 1 hour. But I think for chromospheric lines and also the carbon that it seems that is optically thin, I think it's better to have very, very dense grid, because then you can cover fluctuations from one atmosphere to the other better.
Because my main point is that I'm a little bit cautious, let's say, or skeptical to show this plot, like, because this is what I'm telling these lines are sensitive based in the response function that I obtaining, but it might be depend of the sampling. So that's what I was just like, is this very, that's why I say roughly,
Yes.
But okay.
Yes. Yes.
Okay, yes, sorry for this.
No, I think it's good, and I think Han wants to add something.
Yeah, I think that the results don't much, change when you change the sampling. It's just you get better looking graphs, but I don't think the essence of the what you get changes a lot. It's just numerical. You have more numerical, a little bit more numerical inaccuracies as you.
But I think the interface between when you have sensitivity and when you stop having sensitivity should be better defined, right?
Yes, but you have to think about what the response function or what it actually means, because you take one snapshot in time or one pixel, and you get a range of values of where the line is sensitive, but it changes with every moment and every pixel. So, I mean, it helps you. I think you should see it as a way to help you understand the physics of where in typical conditions you are sensitive, but you shouldn't put like 1563 kilometers as the height of which is sensitive, right? But that doesn't make sense.
Okay.
Yeah.
So, but still, I think, Alberto, it's good that you show us this, and I think if you have the time and try to have it with a dense sampling, maybe for just one case, maybe reference case, I think it's good if we see it, for example, next week and next class, and then we check if things look smoother. That I hope it will look, and we can try to.
When is the next? When is
I
the
think
next class?
In 2 weeks. In 2 weeks.
Okay, that is Thanksgiving, Black Friday, more precisely, I think.
Okay.
Just letting you know.
Okay. Well, we will see. But I think it's good that you ask us, and I think you should give it a try and then check if things are different.
Yeah, I will try that. I will increase the sampling in the model atmosphere. And
yes.
Okay.
Okay. I think Ryan.
Thank you very much.
Thank you, Albert. Ryan, do you want to ask something else?
I was just wondering, while you were talking there, is there any concept of an uncertainty in a response function?
Is the other way around? You use the response function to calculate.
Yeah, no, but I think
I
understand
was
the
just
question.
wondering, why would you go super high resolution in optical depth if you don't really know how sensitive you are in that resolution element? Do you know what I mean?
Well, I think I'm mixing things. So I think you can go high, as I said, to at least have a better interface. So you don't know where the interface between sensitivity and non-sensitivity will happen. So if you have a uniform high dense optical depth, you will always see it, depending on the atmosphere that you choose. You will see when it stops being sensitive or not. How practical or useful is that? I think it depends on who you ask, but I think it should be okay if you try it for a few atmospheres to have a high density optical depth sample or geometrical height, because the plot will be smoother, and at least this is always nice looking. Now, I think the good question, and I was thinking that is there an uncertainty for the response function? So I mean, we usually use the response functions to establish the uncertainty of the inversion. So the inversion can have an uncertainty given by the inverse of the response function. So if the response function is 0, then you can expect the atmosphere there. You don't know any control of that. And if the response function is large, then you can expect that the atmosphere that you get on those layers, it should be at least until some point accurate, because you have sensitivity. Now the question is, when we are computing the response function, what is the error that we are getting? I think this probably Vasily or Han can add something, because I have never thought about this.
But I think the question depends on the accuracy you are getting with in the synthesis, because the response function is just doing true synthesis.
Yes.
The question is that does depend on two things: on the on the integration model you are using, or the integration tool you are using.
Yes, the scheme.
For instance, you were speaking about the very small step size, but this is because we are using Hermite.
Yes.
Hermite is very fast, but it needs that the step in the absorption is not too large, because it goes with a power 3 or 4 in the delta K. Delta log tau in this frequency.
Yes.
But I think the stick is using
Delo.
modified Delo method that is
like
lower
today.
grade.
Yes.
It's a little slower, but has a better dependence with the step size. Then maybe with a stick you can use a larger step size in log tau. It's a little slower, but but maybe it doesn't need that. The question is that the accuracy in the response function depends on the integration method you are using.
Yes.
Also depends on the line. If the line has a very large absorption, for instance, the chromospheric line in deeper layers, or in the core of the line should have a very large absorption, then the accuracy should be high enough in order to don't introduce spurious results. Coming from the interpolation that is inside the interpolation of the source function that is inside the integration method. I think it's something like
yes, but this also holds for the emergent intensity, right?
Yes, it's the same.
We always assume that the emergent intensity that you calculate is a perfect value, which it is not. It is an approximation, because you have to make some numerical shortcuts. And the other thing that you have to realize is that we assume that you can perturb the atmosphere in one quantity independently of the other ones. In reality, once you perturb only the temperature, you no longer have a self-consistent atmosphere.
Yes.
And so you make all kinds of assumptions that it would take some quite heavy research to figure out how much those errors are.
That's true.
But so I think I mean, no, but given all the uncertainties that you have otherwise, I think it is very useful to do these exercises. But you do have to realize with that the uncertainty is more in the assumptions that you make than in the numerical techniques that you use, in the numerical results that you get.
That makes sense. Thank you.
Okay. So thanks, everyone. Is there any other question or no? Okay. So I think just let me go back to the presentation. Okay. So try to run the examples I prepared as always. Just if you use IDEAL, just run it, and I think it will work. And if not, try to prepare a Python script. I think it should be very easy. This one, I always put a lot of comments, but in principle, only some lines are useful lines are only like 10%. So I think it's very easy to do. Again, as I said, try, if you have time, you can start reading the results and try to make some plot, but we will check how to do it and plot 2D and 1D response functions. And then if you have time, you can pick step 2 or step 3 independently. So you can maybe try to compute the response function for an atmosphere that you have, or from the Bifrost atmosphere. Okay. So then the next class, as I said, it will be loading the results and adapt them to properly presenting them in a presentation or a paper, because we have some error if we just plot the results, at least with the routines I use. And then I think this will not take too much time, so probably like 30 minutes or something like that. So then I probably will use the last part of the class to try to keep it below 1 hour, to show you how to prepare the Bifrost atmosphere for running RH in parallel, using the Python wrap that we had from the previous, that we use also in SER. So the preparation will be almost the same as in class 7, but we change a bit the script at the end to save it in a fits file that follows the Python wrap format. So this will be very easy, so we will do it. And then in the next class, we will learn how to run RH in parallel to compute the same field of view that we computed in day, I think, 9. It took like 2 days. So at this time, if you have a good server like 40 or I don't know, 80 threads, you probably can scale down that to 1 hour or 2 hours. So then it's a very good thing to have the possibility of running things in parallel. And then I think this probably will be the last class of December. We will have the last class for the parallel wrap, and then we will probably start with Decide the new year in 2022. And I think things will be as interesting as they are now, or even more. So if there are no more questions, I just point to Friday 26th that based on Alberto's comment is an interesting Friday. Although here they are talking about Black Friday month, because most of the tech companies, they are offering sales already. So is there any additional question before I wish you a nice weekend? No? Okay, so then thanks everyone. Enjoy the weekend.
Thank you.
Thanks Alberto for the questions and showing the presentation. And I hope to see you.
Thank you.
Okay. I hope to see you in 2 weeks. Bye. Bye. See you.
Bye. Take care.
Bye.
Bye.